All right, so what is today? The 14th. Jeez. The tax day today, I think, is the modified tax day. So anyhow, yeah. The first thing we mean, that looks like we're losing points. So if we're keeping track of the important announcements, exam 2 will be posted today by 1 because Heather asked, and it's due Thursday at 11:59 p.m. So if you have any questions about that, shoot me an email or ask now. It'll be very similar to the first exam. But by the way, to make sure if you go on Canvas, make sure all your grades are updated. I think they're all updated, but if they're not, please let me know so I can put in any grade that you're missing. Check that out. And if you have questions, let me know about that. Yours are missing, all of them? Hold on a second. Let's see. What about I just checked that? Checking now. Oh yeah, yours are, huh? All right. Thank you for pointing that out. I will. Yeah, some of your homeworks aren't shown, but everybody's exams should be showing. Yeah, okay, yeah, that makes sense. All right, interesting. All right, we'll fix that. Thank you for, see, I'm glad we pointed that out. I see that. All right, I will fix that this afternoon. Obviously, I can't fix it right now because we're in class. All right. So, interesting. Wonder why. Some are showing, some aren't. Very interesting. All right. Interesting. I will fix that, guys. All right. Very good. See, I'm glad we look at it and we figure it out. All right. Any other questions? Comments, concerns about the exam? Any homework questions before we start up? By the way, what was I going to say? What did we? Okay, never mind. That'll just sound confusing. All right, so let's pick up then where we left off when we last talked last week. So if we are, hold on one second, I lost my whiteboard. I still can't figure out, like when I open another window on my computer, I lose my whiteboard, which it doesn't make any sense because I don't have it on top of the whiteboards. Someone needs to figure this stuff out before I lose my mind. Okay, so don't forget, last week we missed out on class Tuesday because the internet didn't work. And so we did have class Thursday. So what we did Thursday is we talked about some important ideas. So last week, so particularly last class, we showed some important consequences of the chain rule. And just to remind you of what they were, the first one was this thing called implicit differentiation, and we did some examples of that. And then we gave you some homework problems, and hopefully if you have any questions, you'll ask. And then we also showed how to compute the derivative of inverse functions. So that was the big thing. So really, if we're putting things in perspective, there's really not a function out there that you guys can't differentiate now. We have showed you, or at least given you the tools so that you can now differentiate any function that you might come across. You guys can now take the derivative. So just to remind you of some important formulas that were new to us as of last week, is this important formula that the derivative of the natural log is 1 over x. The derivative of the inverse tangent, the arctan, is 1 divided by 1 plus x squared. And then we also stated the derivative of the arc sine, which is this, and the derivative of the arc cosine, the inverse cosine. Now, these formulas, you know, I wouldn't recommend you memorize them just by reciting them. What I would recommend you do is you do problems, and you do lots of problems until these things become sort of automatic to you, just like 2 plus 2 is 4 is automatic. Does anybody have any questions about these formulas at all? Comments, concerns, any homework problems that you might want to ask about? Going once, going twice. All right, well then, now we go to the next sort of logical step, and that is, now that we can take derivatives, what good are they? Why do we care? Why does somebody want to take a derivative? So let's sort of put it in that perspective. So good news. Here's the good news. So we can now differentiate any function we are given. So you now have learned all the tools. If I give you a function and you follow the rules properly, you can compute its derivative. And so the obvious question is, who cares? Why? Why do we care about derivatives? Well, there's a couple of answers that we can spit out real quick. So first off, well, we know f prime is a rate of change. I mean, that's sort of how we started all this. So this means so if so let's sort of put it in a more practical way. In general, the derivative of a function is a rate of change. But if we put it in a particular context, for example, so let's say, now I'm going to change letters. Let's say I have some function x, and its variable is t now. And let's say that this represents the displacement of an object. Then the derivative dx dt is equal to the velocity. So the first practical application of the derivative is velocity. And then what's pretty interesting is there is nothing that stops us to compute the derivative of the velocity. And so if it exists, we call it the acceleration, which is a word you've no doubt heard before. V prime of t is the acceleration of the object. So this also hits on something we haven't explicitly said yet in class. And that is that if we have a function, we can differentiate it, and then we can differentiate it again. And so then we could do it again if we wanted. Now, we might do this just for fun, or we might do it for physical reasons, like we want to determine the velocity or speed or the acceleration of an object. So let's summarize this because it's quite important. So this suggests we can define the second, third, fourth, etc. derivatives of a function. And so let's make this clear with an example. Or before we do an example, let's actually use the notation. So the first derivative, we usually denote f prime of x, or of course df dx. The second derivative, we might use 2 primes, or we might write it like this, but this gets very cumbersome. And then starting with the third, these prime marks aren't gonna, it's gonna be too difficult. So what we usually do is we use these parentheses like this. Or if we want to use this notation, we might still write it like this. And then of course, this thing goes all the way down. You can talk about the nth derivative. Which we might denote in either one of these two ways. So this is the notation for derivatives, and there's nothing special about how you compute them. You compute them the same way. So to compute the third derivative, I just compute the derivative, then the second, then the third. So let's sort of do a couple examples to help solidify these ideas. Does anybody have a question, by the way? Comment? Quiet. You guys are great. I love it so much. If it's about grades, everybody's happy to talk. But if it's about questions of any other ilk, it's silence. That's okay, though. I love you all platonically, of course. Okay, so let's do some examples. Everybody likes examples. That's the one complaint. You always say, do more examples. do more examples. But that seems kind of boring to me, because that would be like if I was playing basketball and I went to practice and I watched the coach do all the fun. Like, you don't go to baseball practice and watch the coaches play baseball. You play baseball, right? Anyhow. So let's do a couple examples. So let f of x equal 3x squared plus 5x plus the natural log of x. So what is the first derivative? What is f prime of x? Well, that's 6x plus 5 plus 1 over x. What's the second derivative? That would be 6, and then plus 0. And then what is this? Well, the derivative of 1 over x is negative 1 over x squared. And so then the third derivative is going to be positive 2 over x cubed. And then the fourth derivative, so these last couple might take you a moment, is going to be negative 6 over x to the fourth. So we'll just compute the first four. So take a moment to make sure that you understand especially computing the third and fourth ones. Any questions, comments? Okay. Let's do another example. We'll put it in a more practical setting this time. A ball is thrown straight up and its height after t seconds is given by a function. So let's say negative 16t plus 100t plus 5. So I'm not just making this I am sort of making it up, but this formula is actually realistic, and we'll show you soon enough where it comes from. But maybe you guys have had physics before, I don't know, and you might recognize where these numbers come from. But just assume for now that this is accurate. You'll notice that this is a parabola, and its leading coefficient is negative, which means it's upside down. And so what you'll notice is this parabola is going to be very useful in telling us how high the ball goes and whatnot. And we're going to study that kind of stuff in detail soon enough. So its velocity is v of t, which is the derivative of its displacement. So its velocity is negative 32t plus 100. And then its acceleration is the derivative of velocity, which is the second derivative of its displacement, which becomes negative 32. Now, we didn't put any units in here other than seconds, but if you're familiar with how units work, what you'll note is this is 32 feet per second squared, and this is in feet per second velocity, and this is in course in height is in feet. Now again, I'm right now you may or may not understand the basics of the units of physics. We haven't gone into depth in that yet. We will shortly, but right now what we want you to to understand is that in the context of an object that's moving, the first derivative is its velocity, and the second derivative is its acceleration. Does anybody have a question or a comment about this? Okay, so there's some discovery, there's some interesting things that we can learn from this example if we investigate it more. And when we learn from this example, what it does is that it can open our eyes to a much more bigger sort of idea. Does anybody have a question? Okay, so what do I mean investigate this more? Well, let's do that. So these are the things that you want to, if you draw the graph and you do some interesting things. When is the velocity, which is, you will call negative 32t plus 100. This equals 0 when t is equal to 100 over 32, which is the same as 25 over 8. Now, why am I pointing this out? Well, (25 over 8, comma, h of 25 over 8 is the vertex of the parabola. So you guys spent time in previous courses studying these things, vertexes, and you learned how to graph these things. But what we're realizing now is that if we think about this example, and we're going to draw the graph in a second, but if we play around with this example, we start making some connections of things that can turn out to be quite useful for us, as I already alluded to. So if we go to the next page and we look at the graph, which is, it's not hard to graph this. Maybe some of you remember how to do this. I don't know. Some of you might not. That's okay. We're going to learn how to do it using calculus soon enough. Does anybody have any questions before we move to the next page? Comments, concerns? Okay, so let me mistakes I made. Okay, so if we look at the graph, and again, maybe you remember how to do this, maybe you don't, I don't know. But this is a parabola that's open down. And just using a little bit of your intuition and some mental things, you can see that its graph is going to look like this. Now, it's not to scale, but maybe you'll go to Desmos and graph it yourself. I don't know. Let's label some points here. This is the point 0, 5. This vertex, what we found, and then this guy is where it hits the ground here at this T. We didn't solve that, but it hits ground when h of t equals 0. So that's a quadratic equation. You could solve that if you wanted. This is the highest point but it gives the highest point of the ball. And so this point, we know what it is. We know what the t value is. We found it to be 25/8, which is a little bit bigger than 3. It's like 3.125. And so h evaluated at 25/8. So we're kind of like playing around with this, which if you plug it into the calculator, you're going to get what? 161.25. This equals the maximum height of the ball. So if we think about the physical characteristics of this, and I draw some arrows, here the ball's going up, and then now the ball's coming down. So remember, we're not saying the ball's moving along this arc. We're saying this arc gives the model of it goes up, hits its highest point, gravity wins, and then it falls back down to the ground. Does anybody have a question, comment? Do you want me to point something out? Are you confused about something? One thing I will point out is, notice I didn't ask a question here. I just said, here's a function. Let's put it in this context. Now let's investigate. We're investigating. We're being scientists. We're trying to learn from a picture. We're trying to learn from derivatives. So in the physical context of this problem, we learned something else. And this is also important. So the maximum height also occurs when the derivative, which is the velocity, equals 0, which should match our physical intuition. Because if I throw something straight up in the air, what's its velocity at its highest point? Well, it's got to be 0, because it's no longer going up and it's no longer coming down. It's not moving. It when it reaches its highest point for that one instant, it is fixed. And so its velocity is 0. Does anybody have a question or a comment? All right, so what's the bigger picture here? What is sort of like a consequence of this? What do we learn from this? You're going to say, some of you are going to say, oh, hold on one second, guys. Hold on, guys. Give me 30 seconds. My kid just woke up. It's up to you, whatever you want to do, okay? Let me know if you hear your sister. Okay, thank you. This is it. Welcome to the quarantine world. Or no, we're not in quarantine anymore. Not yet, at least. We might go back. That was Lydia. She just woke up. She's going to go watch her Kindle now. All right. Pardon that. Although you can't be mad about that. There's far more things you can be mad about. Like you're looking at my kid's playroom. I have a t-shirt on. I don't even know if any of you guys are awake. For all I know, you guys are all sleeping. Okay, here we go. I love when I say that. Now everyone's like, I'm awake. How about a joke for Lydia? This is a good one. Let me see. I don't know if I know this one. What do you call a bear with no teeth? I don't know. That's a good one. I'll have to use that on her. She'll like that. Thank you for sharing. All right, back to the math. So this is good. Okay. Okay. All right. Man, I need to get back in a classroom. Okay, so what is the moral of all this? So the last example suggests that, and it's not just its example, it's our physical intuition. It's our intuition of the world we see. And I would encourage you to think of this example of something going up and then falling back down. I mean, humans have been curious about this for as far back as we have written history, and it's surprisingly enough, we didn't know anything about it until the last 400 years. So if you think about how long humans have been on this planet and how long it took us to be able to sort of quantify and understand how something as simple as a ball goes up and comes down. But anyhow, it literally took humans to invent or discover calculus for us to explain it. So anyhow, what does this last example suggest? So it suggests that the derivative holds the information about the shape of the graph. And let me be very clear here. So let me, because that might seem a little unclear. The derivative holds information about the shape of the graph of f, of a function. So let me say this in a more specific sort of way. That is f prime, and for that matter, we're going to see f double prime. Tell us everything about f. So let's imagine, let's go from an example of that ball going up and down. Let's think of something even more practical. You own a business. Your likely ultimate goal when you own a business is to make as much money as you can, right? Some people might say, well, I want to serve a customer. Well, okay. Let's just assume we all want to make money. So your goal as a business owner is to maximize your revenue, correct? Maximize your revenue and minimize your cost. Now, anybody who's studied economics or business knows that that's not a simple thing to do. But in a very sort of, I don't want to say abstract way, but in a practical way, you might have what we call models. And these are big, fancy, scary functions that help us describe our revenue and our cost. And what we're saying here with this moral is that suppose you have a cost function. Your job as an analyst or as the mathematician would be, okay, how do I minimize my cost? Now, you might be sitting there and saying, what do you mean minimize my cost? Well, I don't know. Suppose you manufacture things and you want to sell them. You have to make decisions like, how much do I sell them for? How much do I pay my employees? I mean, you can imagine all the different variables. But if you're thinking of a simple case, imagine you have to sell lemonade on the corner of the street. Do you go to the store and just buy 1,000 lemons to make lemonade, or do you buy 10 lemons? How many lemons do you buy? Well, of course, you know that's going to depend on how many people do you think are going to want to buy your lemonade. And then once you determine how many products to buy, then you have to ask yourself, how much do I sell my lemonade for? If I make it too expensive, not enough people are going to buy it. But if I make it too cheap, everybody will buy it, and then I won't make enough money to cover my cost. So you understand that there has to be some optimal value, at least theoretically out there. There's an optimal value. And so what we're saying with this whiteboard right here is I'm saying one of the key sort of practical applications of the derivative is it allows us to determine optimal things. So let's get in detail about that. Does anybody have a question? So let's draw a picture to maybe make this even a little more clear. So let's draw this guy, and here's my axes. Let's draw a picture. Let's look at something like, just going to draw some generic function. Now, it's convention in the English language and many other languages that we read left to right. So what we want to do a few things is we want to look at this blue curve, and let's imagine we're walking along it or we're riding a roller coaster. I mean, if I ask some kid in 5th grade to describe this curve, what would a 5th grader say? A 5th grader might say, well, it's going down, and then here it's going up, and then it's going down again, and then it's going up. So if I label some points, like maybe I call this point, let's I don't know what this is. Let's call this, we'll call this point A, and then here we'll call this point B. And then if we look at the tangent lines, so I'll draw them in red. Sort of what we want to think about, and there's lots of things that you can describe, as I said, with this picture. You could say it's going down, then it's going up, and then it's going down, and then it's going up. And I guess I should even label this point because this guy is the same as well here. So let's call this C. Call these 3 points A, B, and C. So So the tangent lines at A, B, and C have slope 0. And so there's lots of things that we could say. We can say, okay, here's an interesting thing we notice. At those points A, B, and C, we can give them sort of intuitive English descriptions. We could say that this is a minimum value. We can say this is a maximum value. This is, and C is a minimum value. We could also say things like it goes from decreasing to increasing, or it goes from going down to going up. There's lots of physical ways we can describe this picture. So, you know, if I said to you, take 5 minutes and write down all the physical descriptions of this blue curve, there's lots of things you can write. There's lots of sort of conjectures you can make. So one thing I could say it's also similar is f prime of x equals 0 at those points. Another thing to look at is not just the slopes there, but let's look at, say, the slope at some other points. If I look at the slopes, let's label this guy. Let's take this point. I'm going to draw a point here. I'm going to call this, what am I at? C. So we'll call this D. We'll call this point E. And then I'll call, this point F. And then lastly, we'll do one over here too. We'll call this G. So I'm going to take another color and I'm going to draw some tangent lines. So for example, here, the tangent line at D looks like this. And then at F, it's almost going to cover the curve. And then at the other 2 points, I'll use a different color. So, oops, that's not good. So here's another thing to notice. On these points, so the green tangents have positive slope. The slope of those lines is positive. And if you look at the pink ones, the pink tangents are negative slopes. So what this beautiful picture of colors is really telling us is it's telling us that the behavior of the function f is completely determined by the sign of the derivative. If the sign is positive, we have one behavior. If the sign is negative, we have another behavior. And if the derivative is not negative or positive, but 0, then we have a third possible behavior. So my advice would be for you to think about this picture and ponder it. And not only say how great of an artist I am using this crazy pad and pen. It's really difficult. I'm just kidding, of course. But no, think about this in context of what you know about slopes and derivatives. Does anybody have a question or a comment? Okay, so before we move to the next page and start making definitions, let's again revamp what a fifth grader might say. A fifth grader, you know, if we might say describe this, you know, maybe, let me get my little arrow. Maybe a fifth grader says it's going down, 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 down. Then I hit a smallest value. Then I go up, 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 up. Then I hit the top of my mini mountain. And then I go down, 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 and I hit the bottom of my valley. And then I keep going up again. And so we need to make these ideas precise. So that's what we're going to do next. So let's do it. So the first thing we're going to do is we're going to use our sort of geometric intuition here. We're going to give a name for this type of problem, and then this type of problem, not problem, excuse me, this behavior. Like if we look at A and C, we notice that A is at the bottom of a valley and C is at the bottom of the valley. But the Y value at C is a bigger number than the Y value at A, at least in this particular example. And so we want to be able to distinguish these things. So what we have to do is we have to have some sort of precise definitions. So that's what we're going to do. So let F be defined on some domain, we'll call it D. If, so this is going to look scary. If F evaluated at C is greater than or equal to F evaluated at X, for every X in D, we call F of C an absolute or global maximum of F. So this is a precise definition for what you see on the previous page. So what you need to understand here, and we're using more context, is that C is some fixed number and X is a variable. So let's be very clear here. Now we're going to say if F of C is greater than or equal to F of X, for each x in some interval containing c, we call f of c a relative or local max. So now you have two types of maxes. You have a global one and you have a local one. So the analogy here, or the metaphor, or whatever, is, let me look in this room. In this room right now, there are 8 of us. I'm assuming I'm the oldest. I'm 40. So relative to this class right now, I am the oldest person in this Zoom meeting. But I'm surely not the oldest person in Allegheny County or wherever you guys are at right now. So relative to this Zoom meeting, I am the oldest. But relative to all the people who live in Allegheny County, I'm not. So if we look at a picture, it'll help make these ideas a little more clear. Before we do that, we should, in a similar manner, we can define global and local minimum. We're not. So the best way to think about these are through examples. So let's just draw a picture. So imagine it comes up, comes down, goes up, and then comes back down again. So what can we say about this, the way I've drawn it at least? So the way I've drawn it is we have local max at, we'll call this A. We have local min at B. And then we have global max at C. And the reason I'm saying it's global is because its y-coordinate is higher than the y-coordinate at A. So A is the maximum relative to its neighbors in its local area. It's bigger than everybody else, but it's not bigger than everybody. It's only the biggest, or the highest, I should say, in its local neighborhood. And clearly the way I've drawn this, another thing that you need to notice is this particular function has no global mins. Because remember, when we draw a graph like this, it's assumed the convention is we assume that it just continues its behavior in both directions. So there's no smallest value for this function, but there is a largest value. Does anybody have a question or a comment? Okay, so the big question and the one of the most practical importance is, how do we determine these points? If I just draw a curve, well, then it's clear by our eyesight what the point I'm trying to make here. But if I give you some function, perhaps a complicated one, then it's not exactly clear what the maximums and the minimums are. You might recall when you were in a pre-calculus course or a college algebra course when you learned how to draw and sketch the graphs of functions. Without calculus, the best that you could often do was just find the places where it crosses the x-axis. And you had to estimate all these other points. I think in those classes they call them turning points, I believe. I could be wrong. So you would have to estimate these things. But now what we're going to say is with calculus, we can precisely determine these values. So let's state that. So and by the way, when I say practical importance, I'm not just making that up. This is a very, very useful tool in the real world. Given a function f1, does it have any max or mins? And then more importantly, actually, if so, how do I compute them? So the first thing we want to know is if they exist, and if they exist, how do I determine their precise values? Okay, does anybody have a pregunta? Okay, I've given you 10 seconds. So here's what we know. And this is from our example going way back to the ball. One of the things that I hope you'll go back and ponder, and I hope it will connect with you, is the following. So luckily, we have some fancy theorems to help. It's always good to have fancy theorems. The first one is what's called the extreme value theorem. And what this theorem says is it's a guaranteeing when something is going to be there. So in math, we often have these theorems that are of huge theoretical importance, because this theorem is going to tell us that something is going to exist. We just have to figure out how to find it. That's important to know, because there's lots of times where if we go looking for something and it doesn't exist, it's a big waste of our time. We don't want that. So what does the extreme value theorem say? So if f is continuous on a closed interval. So remember, how do we write a closed interval? We write it like this. That means we are including the endpoints. Then it has a global max and min on that interval. Now, if you draw a graph of something and restrict it to an interval like that, that makes sense. So this is a very deep theoretical theorem. Yeah, it sounds funny, but it's a theoretical tool. And what I would encourage you to do is think about this theorem and think about the hypotheses. First off, that f is being continuous, and then also that we're including the endpoints, because if you don't include the endpoints, then this thing could fail. So here's what I mean by that. To help you understand, I would encourage you to do this. Consider the function f of x equals 1 over x on, notice I can't close, let me write that more clearly because that looks bad. This function is not defined at 0. So notice this interval is half open. It doesn't contain 0, but it contains 1. So graph that function and think about it. Does it have an absolute max? Does it have an absolute min? Think about it. Just look at the picture. Don't worry about anything else. Draw it. Look at the picture. Okay. Then our next useful theorem, depending on what book you read, is called Fermat's theorem, named after this famous mathematician, Fermat. So let's draw this one down. So this is going to be the one we really use all the time. So suppose, okay, all right, guys, give me 5 seconds. I'll be up. Give me 5 seconds. I gotta get my kid. My mom's not here yet. Give me 5. Sorry about that. We have chaos has ensued in the O'Grady house, but it is calm for now. Okay, so let's get back to this. So if we reset real quick, we have a function, and the big question is, does it have a max and a min? And if it does have one or the other, how do we determine them? So what these previous pictures and these examples were trying to motivate, at least that was my point, helping you to motivate and understand if we study them enough, is that we see certain things. So one of the things we recognize right away is the following, and that is if F has a max or a min. Now notice I didn't say it has to be global or whatever. I just said that it has a max or min. So when I don't use the adjective of local or global, then you can assume it can be either. So suppose F has a max or a min at x equals c and F prime of c exists. What's the conclusion? The conclusion is then that the derivative has to be 0 at c. And this is what we already saw in those pictures because the tangent lines were straight. They were flat. Slope 0. Slope 0 means derivative 0. So this seems like it makes sense to us if we understand those pictures and the examples that I've been talking about for about an hour now. So this is great news. Great news. So in many ways, this means solving F prime of x equals 0 is the key to finding max and mins. That's what this theorem tells us. It's telling us that. Heather, yes. I don't know. The book probably calls it something like that. Yes. It doesn't. Okay, so look, technically no. Okay, so here we're getting into a technicality. So Heather asked the question, does the book call this the local extreme value theorem? My guess is it does. But it's technically, well, I mean, some books call it Fermat's theorem. But your point about in the book, it probably says, notice I wrote, suppose F has a max or min at x equals c. The book probably says, suppose F has a local max or min. Is that what you're telling me it says? Yeah. So that is just a technicality. Look, if you wanted to imagine that I'm restricting my function to an interval like 0, 1, where I'm closing it in, then depending on how you define your derivatives, the derivative can't exist at the endpoints because, unless you consider what we call, we had left and right limits, which means if we wanted to, technically, we could talk about left and right derivatives. But these are technicalities that aren't going to bother us in a Calculus 1 course. Does that make sense? So if you want me to be very much agreeing with the book, let's do that. Let's put the adjective local here. That way, I'm not confusing you. How does that sound? So again, let me reiterate that point. The book is just covering its behind, because you could argue then, well, what about if I restrict my function to like an interval, and then if the max, just think of x squared on 0, 1. So let me just draw what I mean real quick, and then I'll delete it. If I look at x squared, but all I do is restrict myself to the interval 0, 1. So here is the global max. Here is the global min at the endpoints. Well, then you could argue that since I'm not defining it outside of 0, 1, that the derivative doesn't exist at those endpoints. Does that make sense? I don't know, maybe it doesn't. Look, don't let this stuff, you know, wear you out. It's just a technicality. Did I make things worse, or did I clarify for you? I don't know now. I hate when I make things worse. All right, cool. I trust you. Okay, so for us in Calculus 1, what we want you guys to understand is what I just wrote, the last sentence. Solving that equation is the key to finding max and mins. Because what it's telling us is these are the candidates. The solutions to f prime of x equals 0 are the candidates. So since they're the candidates, we give them a name. So let's state that now. So solutions to f prime of x equals 0 are called critical numbers. Now, some books probably say critical points, but that's misleading. I like to call them critical numbers. Some books also say that you're a critical number if f prime of x does not exist. So let me clean that up. So let's be a little more clear, because that insinuates that the whole function doesn't work. So if f prime of c does not exist for some c, we call c a critical number as well. Does anybody have a question? So what this means is this is very, this is good news for a certain problem. So the above theorems allow us to, now I'm going to put this in quotations because it's very relative, to easily determine global max and mins. It's very procedural. And we're going to do an example in a second, but let's think about how we can do this. The first thing you do is, let me be a little more specific. That's still misleading. This is global max and mins on a closed interval. But this is okay too, because many practical problems we're dealing with closed domains, so it's not like we're cheating here. So instead of me just writing it out, let's do an example first. And again, I'm putting the word easily in quotations because it's relative. It's only easy if you understand what we're talking about. Now, for many of us, that takes some time to understand. All right. Does anybody have any questions before we continue this? Okay, so let's do an example then. I keep things are disappearing. So let's go to the next page. So determine the global max and min of, say, f of x equals, let's pick a good one, x cubed minus 3x squared on -1 to 3. Okay, so so here's how we're going to do it. We're going to use some deductive reasoning. So first, so let's determine the candidates by solving f prime of x equals 0. So what's f prime of x equals 0? Well, that's the same thing as 3x squared minus 6x equals 0, which is, if you factor out a 3 and you factor out an x, you're left with 3x times 1 minus 2, I'm sorry, 3x, this is an x out here, equals 0. So the candidates are, or the critical numbers are, if you will, are x equals 0 and x equals 2. But one subtlety is, since we're restricting our domain, we have to also consider the endpoints. So second thing we have to do is note the endpoints the endpoints of x equals -1 and 3 are candidates too. So what we have to do now is we have to just evaluate the function at all four of these values and see which is the biggest and see which one is the largest, or excuse me, the smallest. And then we have our global max and min. So lastly, we are going to compute, or maybe a better way of saying it is evaluate. Sweet. So lastly, evaluate f at the candidates. So what are our candidates? The first candidate is f of what? -1. The next candidate was f of 0. The next candidate was f of 2. And then the last one was what? F of 3? Is that what we? Let's double check. Yeah, -1, 0, 2, and 3. Okay, so what is f of -1? Well, when you plug in -1, you get -1 minus 3, so you get -4, right? Is that correct? I think it is. All right, so yeah, f of -1 spits out -4. When you plug in 0, it spits out 0. When you plug in 2, it spits out -4. And then when you plug in 3, what does it spit out when you plug in 3? So 3 cubed is what? 27, and then 27 minus 3 times 9 is 27 minus 27. So it's also 0. So this is a very interesting function. It might be worth your time to graph it. So what we notice is the following. We have global min at 2 points, at x equals -1. Let's write this a little. Let's write it more specifically. So what's the point? The point is we have one at -1, comma, -4, and 2, comma, -4. And then we have a global max at 2 points. Where does our global max occur? The first one is at 0, 0, and we have another one at 3, 0. Does anybody have a question about this? So if you look at a graph and say you go to Desmos and graph this, you'll see that what we just found by hand, what we found analytically, will be confirmed when you look at the graph. Comments, questions, concerns? All right, so that's the end of that example. And so while these ones are quote unquote easy, I don't want to say easy, but compared to everything else, they're relatively easy. We have to do more work. So the problem of determining max and mins without domain restriction is more difficult. It requires more theoretical tools. So notice I'm saying without domain restrictions. What do I mean by that? Well, in this problem, we were restricting our domain to -1 to 3. So in essence, by restricting our domain to a closed interval, a comma b, the problem is easier. But if I just said to you, determine any max and min for this function f without restricting the domain, it would be a little more difficult. Perhaps there's more out there that are outside of this domain. Perhaps there's not. We don't know. So the problem of determining maxes and mins in general requires more fancy tools. So anytime I use the word fancy tools, we think of that as theorems. So the main theoretical tool is called the mean value theorem. So the mean value theorem is the theoretical centerpiece of everything. And once we have this theoretical centerpiece, we're going to get all these consequences that allow us to, I don't want to say easily, but they allow us to have a systematic way of determining maxes and mins. Okay, so what does the mean value theorem say? Well, let's draw a picture, or maybe Let's draw a picture. That'll be good. And we'll end it with this. So if we draw a picture, make our little axis here. So let's draw a typical looking function. And let's assume it looks like this. So now I want to pick 2 points, and we'll call them creatively A and B. And what we're going to look at is we're going to look at a couple things. So first off, let's note that this blue curve, this has got to be some function, the graph of some function. So we'll say it's y equals f of x. And now I'm going to look at a line. In particular, I'm going to look at the line that goes through the point that I drew. So let's look at some interesting properties here. I am going to label another point. Now just use your intuition here for a second. Don't overthink it. If I use my intuition, if I look at this point right here, which I'm going to call C. And so now I'm going to draw a pink line. I'm going to tilt this a little bit. So if I look at here's what the mean value theorem is saying. By the way, this is C comma f of C. And of course, this is B comma f of B. This is A comma f of A. So the thing that is, and maybe the picture's not great, but hopefully the mean value theorem says the following. So the slope of the green line equals the slope of pink. So let's change colors here. So that's what I want you to, the picture at least is trying to show you that. And you can theoretically prove or mathematically prove this. And what's even more interesting is if we write this in terms of the algebraic and the calculus language, if we write this in that language, what is the slope of the pink line? Well, the slope of the pink line we know is, by definition, of the derivative f prime of c. Now, what is the slope of the green line? Well, the slope of the green line, by definition, is it's y1 minus y2 over, x1 minus x2s, or in terms of the function language, it's f of b minus f of a all over b minus a. So this is what the mean value theorem is saying. It's saying you can always find this point C. So let me write this down. So the mean value theorem says the point C satisfying the above formula exists when f is continuous on a comma b, and I'm running out of space and they don't give me a 21st page. This is ridiculous. If it's continuous on a comma b and, I'm sorry I'm squeezing this in, and differentiable on the open interval a comma b. So this result, which is very overwhelming to a calculus student, so please don't stress out about this. I'm not going to ask you on the test to well, I shouldn't say it. I might ask you something about it, but that would be one of the harder problems. Really test to see who's a legend. But this is a theoretical tool. This tool is going to be used to develop all these other things that you're going to be able to use and calculate with. Does anybody have a question or a comment? Again, I hate squeezing this in like this, but Zoom only gives me 20 whiteboards. I don't know why. Probably, actually, I do know why, because I forget. I went on a Q&A and they were like, nobody should use more than 20 because the audience is bored at that point, which is a good thing, right? You're bored already. You're stressed out. You're like, just give us the test, oh great. But look, don't forget, in my ideal world, which I can't force you guys to do this, I really hope that you will try to learn this and take the time. It's not easy to learn this, but it's a lot easier for people now who are attempting it because you have so many resources, YouTube, Google, all the technology out there to help you learn and understand. So does anybody have a question about this? Comment? All right, well, listen, then I guess we will end it here. I'm happy to answer any questions if you have any. Otherwise, I will say check Canvas shortly. I will post it no later than 1, the exam. And if you have any questions at all, please email me if you want to meet. I'd be happy to. Oh, yeah, so I don't intend on having class, but I'd be happy to meet if you have any questions. So there'll be no class Thursday. I would say use that time, but I'll be around if you want to ask questions and you want to Zoom for exam help or whatever. Feel free to email me. All right. Do you want to have class Thursday? Now, if you say email me and say, yes, I want to have class, I'd be happy to have class. But I figured I'd give you guys a break from new material and you can work on the test. That's my idea. So take it as that. If you want to meet, feel free to email me and I'd be happy to schedule a one-on-one or whatever at any time that works for both of us. Any other questions? All right, gang. Well, listen, thank you very much. I hope you learned something, and I hope you'll try to learn this. It's really fascinating if you dig into these proofs and stuff, which we really don't sort of do in a Calculus 1 course, although sometimes we have done some proofs. Anyhow, thank you guys. Good luck on any exams you might have, or if you're on vacation or whatever it is you're doing. Have a good time. I will talk to you all sooner than later. Good luck. Thank you very much.